All right, it's semester 1 2019 and faithful few people are here in Rennie Lecture Theatre to talk about Algebra II, and we're going to see if we have some things to talk about, and we'll muddle through them mainly to show it's possible to figure these things out if you don't already know. So let's see how we go. Actually, before we launch into anything, you might have some stuff ready, but what's in Algebra 2? Like what's the course about? And we can write some of those things down. Just want you to tell me.
Groups and vector spaces.
That's pretty much what the course is about. Okay, what sorts of things did we find out about groups?
What a group is.
Yeah, we had a definition. Obviously, you mentioned isomorphism earlier, so we had that. Okay. Anything, just trying to brainstorm things that are in the course, because it's not a bad thing to try and remember stuff since you have an exam in which you're going to have to. So, anything else? What else did we find out about groups?
Kernel and image.
We had kernels and images of things. What did they go with? Homomorphisms, is that what they're called?
Yeah.
Okay. I reckon we would have done something on subgroups. Would have been things about subgroups. Yeah. And most of these things would have had some theorems to go with them about yeah.
First article.
Okay. All right. With some theorems, it'd be useful to know what those theorems were in a minute when we're up to them. Were there any particular kinds of groups? Like specific kinds that were talked about? Like terminologies? Were there different kinds of groups? Sorry?
Factor groups.
Factor groups. Any other words we have to describe groups? There'd be abelian. Abelian would be a word that was used to describe groups. And cyclic? Is that a word that we use? Cyclic doesn't sound very well. It's like calling someone who rides a bike a cyclist. Sorry? Quotient? And actually, that just reminds me, there would have been all these things on permutations at some point. Was that in this course?
Yeah.
That would have been way back in the beginning. At the
Yeah.
Right.
Yeah.
I'm just doing a bit of brainstorm with what's in the course at the moment. Okay, well, if we think of anything later, we can add it. What's in vector spaces? There'd be a definition, obviously.
Subspaces.
Sorry? That means there's norms and dot products. What are the dot products? Inner products.
Yeah.
Yeah.
All the things with the span and the basis dimension.
What's the matching idea for isomorphism over in vector spaces called?
Isomorphism.
It's still called isomorphism?
Yeah.
What's the matching idea for homomorphism over in vector spaces? Sorry?
Linear function, we also call homomorphisms.
Also called homomorphisms, okay.
Or yeah, linear transformations as well.
Okay, so are there any, do you make vector spaces?
Yeah.
We do that too?
We did projections as well in different spaces.
Were there any special vector spaces? Yeah. No, adjoint is one of these linear transformations, though, isn't it? Okay.
Group spaces.
Okay.
Everything in groups, we forgot everything. So it's actually in the test we did dihedral groups and orbits.
You like group actions as well?
The group actions and tests. Yeah, that's the two things that are in the exam. That's actually in the exam. The last two, yeah.
Okay, so what is actually in the exam for groups according to the lecturer?
Just the last two things. Just the last two things you wrote.
The group action?
Yeah.
And dihedral groups. Yeah.
Groups
and symmetry, symmetry groups, symmetric groups as well.
That stuff?
Maybe plastic groups.
So when you, we'll talk about that in a minute. So when you say symmetry groups, do you mean groups that are symmetries of objects?
Yes.
Because it includes the symmetric groups.
Sorry?
The symmetric groups.
Oh, as opposed to the symmetric group. Oh, so the different types of group.
Just as groups and symmetry as well.
Yeah, like functions or whatever.
Okay. Interesting. And then vector spaces is in the exam.
Everything.
Yeah.
Everything.
So there was a test at some point earlier that had this stuff,
Yeah.
Yeah.
and then your lecturer saying all the rest is in the
Yes.
exam.
Okay.
Okay.
It's fixed point sets and isotropic subgroups as well.
And that's under this group action, isn't it?
And orbits as well.
Sorry?
Orbits.
Big points. Okay. Cool. Well, now that we have a list of things to choose from, what are we going to talk about? Sorry? Well, sure, if you want to.
I think really good with this thing.
I will not talk about everything, there is not time. But I'll talk about anything. So, yeah. Last year we did Jordan canonical form and that sort of thing. Was that in this year's course?
Yeah.
So eigenthings was therefore part of this.
Yeah.
Eigen stuff. Okay. All right. So, and I'm just guessing eigenthings in this course are attached to linear transformations as opposed to naturally belonging to matrices per se, but you turn the linear transformation into a matrix if you want.
Yeah.
Okay, just making sure. Just want to know that the idea here. I think I tried to do that in Maths 1B now, which is Maths 1B you probably experienced, where eigenvalues sort of came via linear transformations. But really they just belong to matrices in Maths 1B. Okay, and they really just belong to matrices in Algebra II probably, I dare say. Okay. Can I ask some questions about fields? Did you talk about them in a general way, or did they just sort of, that's brushed under the carpet?
Very little bit.
Yeah.
And just define them, and then some questions and tutorials were like, is this a field?
Okay. Have you done any vector space stuff on fields other than R?
For the complex.
That's
Or
not
the
the
game.
exam, but
That's not the
yeah,
exam.
so that wasn't the case.
Oh, the variation.
Okay.
We did a lot of just generalized, just like F as a field.
Okay.
Towards the end, when I was in products, we just used R.
Okay. So you know what like Z3 is, maybe? I guess in the numbers mod 3, you did modular arithmetic as an example of group stuff. Okay, good. Just checking where the edges are. Okay. All right. So, preferences for things to talk about.
Projections.
Projections?
That's what my vote goes.
All right. Let's go. It would be helpful to have somebody's notes if they are brave enough to let me try and read them. Handwriting can't be any worse than mine. And I'm guessing that one of the neat ways to deal with this is to have some questions from, say, tutes or past exams or whatever about those things, if you have any on hand that we could try and do. Otherwise, I'll Google some stuff and see what we can find.
I've got a one on here, I'm not sure how
That's right. Unless somebody else has physical form, that might be easy. Algebra, substitutes here, more than basis here, and projection is about projections? Yeah, that one. It says projections. Projections. Say it those words. Okay. Projections start. Okay, well I'm just going to look up this definition, which is what it says in the notes at the moment. So we have V as a vector space, and we have Q a symmetric bilinear form. And we have K, which is contained in V, is an n-dimensional subspace such that no, wrong Q. Sorry, I'm so used to writing Q as the rational numbers. Okay, and there exists an ordered basis for K such that this, okay, so this is the beginning information that we had here. And of course we call them V, because why wouldn't we call them K? That would be so much easier anyway. Okay, so, alright, such that they're orthogonal to each other according to this Q, essentially, by the look of it. So Q of V1 and Vj, 0 for I is not equal to j, and it's not 0 when they're not equal. When they're equal, it's not 0. Okay, then we define P which sends V to V by P of V is Q of V just a second, what the hell is going on here? I'm just going to write it down first and see what happens. Oh no, I've got it, yep. Okay, so let me just see what this is. So I just want to see where we're going so far. We have a vector space, we have a symmetric bilinear form, which means that Q of VW is the same as Q of WV. That's the symmetric bit. Bilinear meaning that if we do like A plus B in one of those coordinates, we can expand out over that. And if we go like K times vector in one coordinate, you can pull out the K. That's the bilinear. Okay. Cool. So it behaves the way that dot products behave. Sorry? Okay, so it behaves the way dot products behave as a function. Okay, cool. And then you have a subspace such that Q, does this mean restricted to K? Is non-degenerate. So that's meaning that, so what does it mean to be degenerate? It's turned itself off. What does it mean to be degenerate? Does it mean that everything is zero if it's degenerate? I know, to be non-degenerate there must be a degenerate that is the opposite, which seems to be more useful. What does it mean to be non-degenerate?
If Q of x, y equals 0 for all y, then that implies x equals 0.
That's what it means to be non-degenerate. So this is saying Q of x, y is y for all y, is 0 for all y, then that implies that x is 0. That's what it means to be non-degenerate. Okay. So that means that to be degenerate, there has to be an x that has a dot product of 0 with everything else, even though that x isn't 0 itself. Okay. Good. Just making sure. So basically, if we look at Q just inside the subspace K, we don't have any of these dodgy points that dot product with everything would be 0 without being 0. Okay. So in a sense, you're not allowed to have anything that's orthogonal to everything unless that thing is 0. Okay, well that makes sense. That would be annoying if it happened, I imagine. Okay. Okay, so then there is an ordered basis such that, okay, so this looks a little bit like it's an orthogonal basis.
I just think my best is turning off, so I'll
Turn off the thing that makes it turn off. Okay, so we have an ordered basis, and they, each of them has its Q is 0 for when they're not equal, and so that would mean that they're orthogonal inverted commas in some sense, and none of them is sort of length 0. I would expect it. Okay, and then so we define this thing. So this is the. I just want to highlight where the vector is that's the input of this function. It's there. So basically what we do is that we take our input and we do the dot product in inverted commas of V with V1 and divide that by the dot product of V1 with itself and use that as the coefficient of V1 and do that for all the other V's. Okay. So when we did orthogonal projection in Maths 1B, it was similar to that. Where we did we knew that if we wanted to project into the subspace K, then you would need to have something that was a linear combination of the basis of K. So what we're creating here is a vector that's in K, because V1 up to Vn is the basis for K. So this vector is definitely a vector that's in K, because it's a linear combination of K's basis. And all we have to do is choose the coefficients of V1 up to Vn in the correct way. And this is the way that we are choosing those coefficients. So one of the things that the traditional dot product did in Rn when we were in Maths 1B was it allowed us to, it told us, if we had an orthonormal basis, it told us what the coefficients of the orthonormal basis were back in Maths 1B. So back in Maths 1B we went, aha, well we know the projection has to be a linear combination of the basis. If it's an orthonormal basis, then the correct coefficient would be V dot V1, and that would be the coefficient of V1, and V dot V2, and that would be the coefficient of V2, and so on. And this one, it looks like we're having to divide by the dot product of V1 with itself, because they're not length 1, whatever that means, so they're not orthonormal, they're just orthogonal. But that should be okay.
Because if they are orthonormal,
Yeah. So I feel like this is very similar to what we did in Maths 1B at the moment. All right, let's see if I can get to the end of that. Okay. So, right, this thing is called the projection onto K, or a projection onto K. Characterized by, okay, this is, that's what this thing's name is. Okay? Alright. So this is behaving the way we thought projections behaved back in Maths 1B, but I just want to check some things. So this is so different Qs would produce different results for this. If your bilinear form was a different bilinear form, then it would give a different projection, I would imagine. Okay, so I just want to see what this is doing. So what this does is it takes everything in V and it produces as an answer things that are in V. Okay. So definitely we know that P of V is in K for any V in V, since it's a linear combination of K's basis. So that's something we definitely know is true. So whatever the image of this linear transformation is, I haven't even proved this linear transformation yet, but whatever the image of this function is, it contains K. Like it's not contained K, it's contained in K. Okay? So I just need a picture of this. This is V, and this is V again. And then here we are, this is K. Everything ends up in here somewhere.
Couldn't you write then P as a function from V to K instead?
You could write P as a function from V to K. But it may be important for us to think of it as a function from V to V, because we may be interested in factoring V out by K. Yeah. No, you normally factor out a kernel, don't you? Scrap that. But the point is that until we noticed that it was a function from V to K, it was just a function from V to V. So, yes, you could say it was from V to K, but it may also be important to realise that this is a linear transformation from V to itself, and they have their own structure. I think they form a vector space of their own. I could be wrong about that. I'm pretty sure that the linear transformations from a vector space to itself form their own vector space. Or at least square matrices. Oh, maybe they form a group anyway. Definitely a group. Pretty sure it's a group. Maybe not a group. At least anyway. They have a binary operation, which is function composition. Okay, I'm trying to think of reasons why, but anyway. Over in R3, it's important to realise that a function of the projection of R3 onto a plane is a function from R3 to R3. It still produces vectors that have 3 coordinates. I think that might be what he's harping to. So when we were doing in Maths 1B, projections were still a projection in R3 was still a function of R3. It still produces vectors in R3. They just also happen to be in a subspace of R3. But they still have 3 coordinates. They just also have extra properties. Right. Okay. Okay, so that's what it does there. Let's see what it does to the basis to K. Oh, cool. Okay, so this is going to cancel out. That'll be 1. That's nice. And all the other Q, V, I, V1 dot V, V1 dot V1Q something else is always 0 because we've set up the V's that way. And so all of this is 0 and we just get V1. That's cool. It fixes the whole basis of K. Okay. So since it fixes K's basis, it would have to fix K because it's a linear transformation. And maybe we should have mentioned that it's a linear transformation. I know it's a linear transformation because Q is bilinear. If I replace V with like V plus W, then I can separate the Q, V. I'm just going to go back to that. I don't have space, so I'm just going to put it here. Since it's a linear transformation, and now I'm going to actually show it really is a linear transformation. It really is a linear transformation because when I do this, then because Q is bilinear, I can do this. Plus, I can do it in every coordinate. And that's going to allow me to do this. And if I do that in every one of these terms, I'll be able to pull out the bit that had the V and the bit that had the W. So if I have this bit and all its friends, and this bit and all its friends, then I'll get P of V plus P of W. And it should work similarly with the constants as well. P of like M times V is going to be Q of MV V1 and then I'll be able to bring the M out of that because that's how a bilinear form works. So I'll be able to bring the M outside of all of this. Which means I'm going to get M of PV. So it really is a linear transformation after all. And it's a linear, it inherits that linear transformation thing from the fact that Q is bilinear. The fact that Q is linear in each of its coordinates causes this to be a linear transformation. Okay, cool. We're doing okay. And so because it's a linear transformation, if it fixes the whole of K's basis, then it must fix any multiple of V1, because P of A V1 will be A of P of V1, which is A of V1, which is the thing I put in. And so it must fix anything that is a linear combination. And that, I reckon, is a thing that we could prove to be true of any linear transformation. If a linear transformation fixes a set of vectors, it must fix the span of that set of vectors too. Because of its linear transformationness. That'd be a cool little part A of an exam question, I reckon. If I was writing an exam question, prove that a linear transformation fixes a set of vectors, it must fix its span as well. Yeah. Sorry? Well, you can do it now. You can do exactly what I did here. Okay. So it's a linear transformation, a proper linear transformation, and it fixes the entire of big K, and everything in V ends up in big K. So actually, the image of P is K, because everything ends up in K, and we actually produce the whole of K because everything in K is fixed. So the image of P in fact is K. Is that what we call it, an image? Okay. Since we know the image of P is contained in K, and we also know K is fixed, so K is contained in the image of P because everything in K is the image of something, it's the image of itself. Cool. Sweet. Which means that the kernel would have to be outside K. Because it doesn't, nothing in K produces 0 except the 0 vector because they're all fixed. So the kernel has to be outside K.
Oh, wouldn't K be in, wouldn't see the 0 vector be in K?
It is, but that's the rest of the kernel other than the 0 vector has to be outside K.
Okay, so then, but if the 0 vector was the only vector in the kernel, then the kernel
would be inside K, yes. Yeah. Good point. Got to be careful when you're talking pure maths. So the only vector in the kernel that is in K is the 0 vector, which, as you say, may be the only vector in the kernel. But I reckon the only way to do that would be for K to be the whole of V. If you're projecting onto something, the only way... I reckon if the kernel is... Yes, if the kernel is the 0 vector, it's a one-to-one function. Which means that every vector must produce a different answer, which means that and since things that aren't in K end up in K, and the things that are in K end up in K, that would make it not one-to-one unless everything was K. Oh, it's a proof, we should do that. Prove. Oh, here we go, we've got a thing. Here's a little exercise. Prove. What did we just prove? Prove that the only way that the kernel can be the 0 vector is if K is V. Prove that kernel of P equals the 0 vector implies if and only if K is V. Okay, good. Just want to be, this is a good little proof. So this is assuming all those definitions of what K and P are and V are. So, alright, so if K is in fact equal to V, let's do the other end first. Suppose K equals V, then, so I'm doing the bit I don't know how to do yet because I already know how to do the other bit, I might as well do the hard bit first. So then we know, because based on what we had, so we know the whole of K is fixed, therefore the whole of V is fixed, and actually therefore P is the identity transformation, and fixes therefore only it fixes everything. So the kernel has to be 0 vector because everything is fixed. And so the only V with P of V equals 0 is V equals 0. That is, the kernel of P is just the 0 vector. I'm extremely distressed in this course where we don't underline vectors because I have trouble therefore telling between 0 and the 0 vector, but I'm trying very hard to match with the way your lecturer writes. Anyway, he's just been a bit sloppy about everything. Okay, so let's do the other way. Suppose the kernel of P is the 0 vector. There's totally a theorem that says that if the kernel of a linear transformation is a zero vector, then it's one-to-one. Don't know how that theorem goes, how the proof of that theorem goes off the top of my head right now, but I know it's true.
Does that mean it's then an isomorphism?
Yeah.
Kernel is zero?
Yes. Could still be a homomorphism. Because you could go up to a bigger space and fit a smaller space inside a bigger space. It's a isomorphism between the input, like between the domain and the image, but not necessarily between the domain and the target. Yeah, because the target could be bigger than the image that you produce. But it's definitely an isomorphism between wherever it came from and wherever it's going and wherever it actually ends up. Okay, so kernel of P is the zero vector. That would mean it's one-to-one, which means that what? How do we do that? Just a second. So we would like to show that K is V. So basically, everything in V has to be in K. Yep. See, now I get to the details. I'm not too sure now. So we know. So P is one-to-one. Okay. Actually, if it's fixed, it has to be in K. If a point is fixed, it has to be in K because all of the images are in K. And if it's fixed, it's equal to its image, and its image is in K, which means it must be in K itself. Yes, got it. Okay, we just have to show that everything is fixed. So let V be in V, right? Then P of V, we know that that's in K. We know that P of V is in K. And just a second. It can't be in K. Like, I hate it. I'll hate it temporarily and then I'll love it later. So P of V is in K. Okay. Let us call it K1. But also P of K1 is K1, right? Because it fixes the whole of K. P fixes the entire of K. And that would mean it's not one-to-one unless V is K1. Yep. So since P is one-to-one, that means that V must be equal to K1. Because that's what... yeah, okay. So P of V equals P of K1. So that means that V is equal to K1, because that's how one-to-oneness works. If the output is the same, the input has to be the same, and therefore V is in K. And so the entire of V is contained in K, and therefore V in fact has to be equal to K because K is contained in V. Right. Got it. I'm sure there's a more efficient way of doing that, but this will do. So you'll notice that I didn't write the word it here. It's bad practice to write it in a proof. You should always refer to the specific thing that you're referring to. If you say it, it's not clear what object you're talking about. I mean, it's obvious because it's the only thing in this story that could be, that I could make the statement that it's one-to-one, because P is the only function in this story, but still, you shouldn't say it if you can say what it is. That's just some good writing. Okay. I think most lectures are a little black square at the end of a proof. Yay! Okay, cool. So we now know some things about projections. So I'm wondering at the moment about what the kernel of this projection is, because it has to have one, because it's a linear transformation. And I could at this moment try and figure it out myself, but I could also just look at what the notes say, just to see what they say. Oh, here it is. He's talking about the kernel himself. Look at him. I knew he'd want to. It's a perfectly natural thing to want to do, to talk about the kernel. This says that for any v in V, we can write V is the projection of V, which is in K, and the other bit, which is apparently in the kernel, because if I do P of it, I get 0. Actually, he's used a little swifty here. P of V is the same as P of V, apparently. That looks like a useful thing that we should write down somewhere. So I'm just going to write that down. So where were we? We were in the middle of writing down things that we knew to be true about this thing, and we wrote it in proof. I'm just going to put a little bit back here and go. But that makes sense, I guess, because P of V is in K and K is fixed, and so therefore it has to fix P of V. Okay, that's good to know. So I could probably have reused that fact here, actually. Like P of V is P of V, and so I could have, instead of calling it K1, I could have just left it as P of V in that proof there. It just felt better to give it a name, that's all. Okay, so he said that for any V in the entire of V, V is made of... Okay, well that's just writing 0 creatively, right? We've got plus V and minus P, plus P of V and minus P of V. And then we know that P of V is in K, but also P of V minus P of V is P of V minus P of V, because it's a linear transformation, and we can do that. Linear transformations expand out over linear combinations, and that's the same as P of V minus P of V, because P of V is the same as P of V, which is 0, and so therefore V minus P of V is in the kernel. Okay, so that means, so to sum up, for any V in V, V is P of V plus something in the kernel. Or something in K plus something in the kernel. Cool! Okay, so something in the image of P plus something in the kernel of P. That's cool. Oh, here's him proving that the kernel and the that K and the kernel have to only share the 0 vector. How did he prove that? If V is in K intersection the kernel, then P of V is 0 because it's in the kernel, but P of V is V because it's in K, and so therefore V is 0. That's some bad writing. You really should have said those statements separately, right?
I'll tell you that.
Like he should have said separately that statement. So, 0 is equal to P of V because V is in the kernel, and P of V is equal to V because V is in K, therefore V equals 0. Like that. That annoys me. Sorry, Nick. Okay. So, that's a much quicker proof that we had, but we did a different proof entirely. We went that if the kernel is just the 0 vector, then has to, and then P has to be the whole of it. Okay, and so what we've actually got is that K and the kernel of P are complementary because they add up to V and they only intersect in the zero vector. Okay, cool. So K, which is the image of P, and the kernel of P complementary, i.e. V is K plus kernel of P and K intersection the kernel of P is just the zero vector. Okay, so in some sense they're orthogonal because everything in the kernel of P when I run it through this produces the zero vector. And so the only way that could possibly happen would be for, if you were going to produce the zero vector, the only way that could possibly happen would be for all of these Q of V and V1s to be zero. So it would have to be orthogonal according to this new Q dot product to all of the V's. Yeah. Because being a basis, there's only one way to produce the zero vector, which is if all of the coefficients are zero. So I reckon I'm going to have in my head K and the kernel of P are orthogonal. Since to get P of V equals 0, we need Q of V and Vi to be 0 for all I. Because you need each of those coefficients in the original thing to be 0, or it's not going to come out of the zero vector. It'll come out to something that's not the zero vector if any one of these isn't 0. Because you can't make a combination of those V's to be 0 without them all being 0 because they're independent, because they're a basis.
Does that mean V minus its projection because it's in the kernel, does that mean that's equal to 0?
No, it's just when you do Q of it and something in K, you get 0.
Yeah.
Yeah. So in my head I'm thinking, here's V, there's K, you need more different colours. So there's K, and this is V, and then the kernel of P just makes this in the zero vector. And they're orthogonal down here, there's a right angle here. And everything in V can be made by something in here for something in here. So these form like two axes from which I can create the whole of V. So technically this has, V1 up to Vn in it. And this would have a basis of its own as well, depending on how big K was. Okay, cool. Is there anything else to know about projections? Oh, look, he's even said it's called orthogonal. Yay, orthogonal with respect to the dot product Q. My instincts are good in this course. I'm doing well. Most of what's here, the same instincts that we're trying to develop in Maths 1B apply here. We've just made them more general. We have a dot product called Q, which doesn't behave quite the same way as a dot product normally behaves, but we still call things orthogonal if the dot product is 0. Okay. Suppose that the field is the real vector, and now we're getting into just... This isn't about projections anymore, is it? Now we're getting into stuff about inner products and the Q itself. So did we do anything with projections in any of the tubes and stuff? Do you remember any of it?
We did the projections and find the solution.
So you actually found a projection for an actual thing?
So it doesn't have a solution, so we want to find something closest to that thing in the solution space.
Oh, okay.
So that's it.
Right. So we got to... So you're saying something closest because we define a norm using this Q.
Yeah.
Does that come later? Norms? Did we do norms?
I think we did inner products.
So we have an inner product, positive definite, symmetric bilinear form. So the positive definite bit is this bit here. Let me just go back. Q is called positive semi-definite if Q of x with itself is greater than or equal to 0. Indefinite if there exists an xy such that... Oh wow, so that's such that one of them is positive and one of them is negative. Okay, cool. And it's called positive definite if it's greater than or equal to 0 but it's only equal to 0 if x is 0. Okay, so the only thing with like length 0 is the 0 vector itself. So this projection thing supposedly works even if your Q does these weird things with 0. So even if it's possible for some things to have a dot product with themselves of 0, this would still work as long as you chose your basis so it didn't do that. Because these all had to not be 0. Okay. But if you want your Q to define an inner product, you need it to be positive definite. Okay. Oh wow. I love the function vector spaces. No, from afar, I'm not sure I really want to do much to them, but cool. So this is saying if you have the vector space of functions from continuous functions from 0, 1 to r, then if you integrate them, if you multiply them together and integrate from 0 to 1, then that works like a dot product works. Sweet. It's very cool. Okay. So if you've got an orthogonal basis for which the corresponding symmetric matrix has the standard form, the inner product is called a dot product. Well, it just is the dot product. Okay. Sweet. Okay. So when you did projection, you were saying, well, you're going to find the nearest point on a... I just can't say I'm going to guess. I'm going to guess what this question was.
Oh, it was like... Yeah.
Assignment question, was it?
Yeah.
I just want to do a proper one, if that's okay.
Yeah.
I'm going to make one up. Here we are in R3. And we're going to have K being the set of x, y, z's such that x plus y minus z is 0. That's a perfectly good subspace. And we need a Q. So I could just use the ordinary dot product, but that would feel a little bit sad. We want to do one that isn't the ordinary dot product. So you normally put a matrix here, don't you? To do this Q thing. If you put V as a row vector and W as a column vector and put a matrix here, that will work. As long as the matrix, what properties does this matrix have to have? Has to be symmetric, definitely, because otherwise it wouldn't be.
Is that the matrix where it's got like QV, QV1, QV1, and then it goes QV1, V2, QV1, V3, and it moves along?
Probably.
Because then that's symmetric as well, isn't it?
I don't know what sorts of matrices are allowed here. I'm going to just guess. There you go. That's my cube. Just let me check that it's not. I'm pretty sure the determinant can't be 0. That would be bad, I reckon.
Why would the determinant be 0 bad?
Well, I think if the determinant was 0, then it would be possible to put a vector here and have this come out to be the 0 vector. So if the determinant of this was 0, then it wouldn't be invertible. And if it wasn't invertible, like if you had a matrix, if you have a non-zero solution to this, then the determinant of A is 0. Like it's not, then it's like, if A is invertible, then the only solution to this is x equals 0. If A isn't invertible, then there's a non-zero x to go here. And if there is a non-zero x to go there, then no matter what you put here, you get 0 as the answer. And so we get one of those vectors x that isn't the 0 vector, except that q of yx comes out to be 0 for every y. And we weren't allowed to have that in our theorem to do our projection. So if, just a second, if q of vw is, v transpose aw, and if ax equals 0 for a non-zero x, then this equals 0 for all y, and that means that q is degenerate. Because you said that non-degenerate meant that if that no matter that it was impossible to do this for y transpose ax to be 0 for all y without x being the 0 vector. But if the A is not invertible, then there is a non-zero x that does this, and so therefore you get a degenerate Q. Okay, cool. So I just need to make sure my matrix is invertible, and so this vector is totally not a multiple of that vector. That's all right. And the only way to make this vector out of those two would be to have 3 of this second one and 2 of this first one, which would not put 0 in that spot. Okay, cool. So the columns are not linear combinations of each other, and so therefore it's invertible. Okay, cool. You can see how much hard work it is to write exam questions as a lecturer. But we learned a lot of stuff. If we're going to write my Q as a matrix, it has to be an invertible matrix for this projection thing to work. Okay. I think I'm going to need to put minuses here. Because I think a positive definite matrix has to have the determinant of each major slice being positive. So the determinant of this bit is positive, and the determinant of this bit was going to be negative before. Oh crap, I can't do it. I need to put something in this spot. I can't have a 0 there. I don't need them to be minuses. What I need is to have something bigger than 4 there. So let's put a 6 here. It's easier to turn a 0 to a 6. I need, pretty sure, I'm not 100% sure, but I'm pretty sure I remember something about this first determinant here having to be not negative if I want a positive definite form. But I could be making that up, but it sounds familiar to me. Yeah. Yeah, I feel like there's a theorem that says that. So just to be sure, I'm going to do that. I don't know what the determinant of my big matrix is. It could be negative. But I didn't need it to be positive definite anyway. I just needed it to not be degenerate for this projection thing to work. So that's okay. Okay. So let's see. Basis for K. I could choose 1, 1, 2, and 0, 1, 1. That would work. Both of these vectors are actually in K because they both satisfy K's equation. 1 plus 1 minus 2 is 0, and 0 plus 1 minus 1 is 0. And they're linearly dependent because they're not multiples of each other. And K is totally a plane, so it's two-dimensional, and so that's a basis for K. And how I thought of that, just for your own purposes, I guess some vectors that satisfy x plus y is z equals 0, and I need there had to be 2 since K is a plane. That was how I figured that out, just so you know, in case you're reading this later and going, how did David figure that out? Okay, and I just need to check if Q of those is 0. Which it won't be because all the things in Q are positive, so they should just get bigger, but I'm just going to check. Let us call this V1 and V2. So let's see, Q of V1 and V1. So one of this and one of this is 3. 2 plus 6 is 8, plus 2 is 10, 1 plus 1 plus 6 is 7. So what have we got? We've got 3 plus 10, which is 13, plus 14, which is 27. Sure, well, not 0, so that was all we needed. Q of V2 and V2. I find it much easier to do matrix times column than the other way around, so that's why I'm doing it in that order. So that would be 2, 7, and 4. And so this would be 0 plus 7 plus 4, which is 11. It's not 0. Okay. Cool. Oh crap, I needed to choose vectors that were orthogonal to each other, didn't I? These, when I run them through Q, are not going to produce 0. That's going to be hard, isn't it? I have to do some sort of fabulous Gram-Schmidt process, aren't I? Do they do that in this course, Gram-Schmidt? Yeah. Oh, for the sake of Fred. Okay, we can deal with that. Wow, this is not 0. So 2 plus 7 is 9, plus 8, which is 17, which is totally not 0, so it's not going to work. So I'm going to need to find a second vector that's actually orthogonal to this first one, and simultaneously in the subspace. Sweet. Okay.
We're still just making the question, right?
Yeah. Well, I mean, this is we're now we're doing the question now. We have to find a basis for K. We have to find a basis for K such that Q of the individual basis vectors is not 0, and Q of the two vectors against each other is 0. And that's what the theorem says. Not the theorem, but the definition says. So Well, if I just kept the 0, 1, 1, I would need this to come out to 0. So I basically need like an A, B, C such that 2, 7, 4 is 0, because I need that to work, because this is what I get when I put the Q in there. And I also need A plus B minus C to be 0. So I could choose A to be 11 and B to be 6, and then C to be 17. So this was equation 1, equation 2, equation 3, which was 4 times equation 2. And this was equation 1 plus equation 3. So I'm going to choose A to be 11 and B to be minus 6, and then that would make this come out to 0. And then we have 11 plus minus 6 minus C has to be 0, so the C has to be 5. Make that work. Cool. Alright, so this is my basis vector here. Zero, 1, 1, and 11 minus 6, 5. Sweet. Now I have a basis that works. This is not the Graham-Schmidt process. This was me just trying to use the information I had to figure out the thing I needed. I mean, the Graham-Schmidt process says that you do this dot product with 17, and then you have to normalize things to get length 1, don't you? So I sort of avoided having to normalize anything by doing this process. Okay, so if I choose that as my basis, I will now change the letters to W. Okay, so Q of W1, W1 came out to before 11, and Q of W2, W2 which is 11 minus 6, 5, 11 minus 12, which is negative 1, 22 minus 36, which is minus 14, plus 5, which is minus 11, and 0 minus 6 plus 15 would be 9. So we get minus 11 plus 66 plus... For the sake of Phil! No, it's minus 9. No, it's plus 9.
I think the minus 11 is something.
Is it a plus 11?
No, it's something else.
11. So 22 minus 36.
Minus 14. Minus 14 plus 5. Is that minus 9?
Can I do that? So we'll go 22 minus 36. Is that a minus 9 then?
Yeah, okay.
22 minus 36, which is minus 14, plus 5, which is minus 9. Okay, gotcha. So 6 times 9 would be 54. It's still wrong. My minuses are wrong. The numbers are almost right. This is supposed to come out to 0, people.
Okay.
It's not supposed to come out to 0. It's supposed to come out to... It's supposed to come out not 0. It doesn't matter what this is. It's okay. Okay, so this is 88. Okay. All right. And so now, therefore, my P of V is Q of V W1 over the length of W1, which was 11, times W1 plus Q of V W2 over the length of this, which is 88, times W2. And that's what the projection function is. Okay, I think I get it now. I've got myself a little bit. I thought I was trying to make it come out to 0, but I was doing W1 with W2 with W2. But what I really needed to check is if W1 and W2 really were orthogonal, just to be sure. I just want to make sure about this. So what was my vector? 11 minus 6, 5. 0, 2, 0, 6, 7, 4, 22, minus 42. Yep. Okay, good. Just wanted to make sure they're really orthogonal. So this really will work as a projection, and everything that's in this plane should come out to whatever it was to begin with. And everything that's not in this plane should end up as something in this plane. And in fact, it should be orthogonal with respect to Q. Okay, I think I can actually make something that does this now. I feel comfortable with what this concept is. I don't know how you feel, but I now know that if I have, the tricky bit is really this bit here, where we have to choose a basis where they're orthogonal with respect to the Q. And that's going to be hard, finding things that are orthogonal with respect to the current inner product. Okay. Right, how are we feeling? I think I know what this is doing now. Now this is just, I can tell you what's going on in my head. In my head, I have what projection used to be when I was in Maths 1B, and I'm replacing all my dot products with Q's. That's what's going on in my head. Okay. So, what do we want to talk about now? While you're thinking about it, I do have a comment on this, and this is just how reading pure maths goes if you ever want to read a pure maths book. They just assume that everything they say where they define stuff is understandable at face value. So this definition of what P was, it was just there. Sort of no real motivation, it's just a thing. And you had to make sense of what each tiny piece of it meant to get a handle on a feel for what it was doing. And I don't know if you noticed what I was doing. Every time I did that, I went, oh, what do all these words mean? And I kept going back and forth to where I was up to and where I had been as I was trying to understand it. So just for future reference for pure maths, or any maths actually, it's useful to do that, to go back and forth and to say, well, what does this mean? How do I feel about it? What can I say about this? And you saw that my general Tigger-like approach of bouncing around, of going, oh, I think I can prove something. I'm going to try and prove something because it's useful to try and prove things. I thought of this thing that I think is true. Let me see if I can write a proof. And it's my usual way of studying these courses, which is probably a bit late for this stage of the game, but for future maths courses, not the worst plan. To spend a little bit of time going, I'm going to attempt to prove something that I've thought of that I reckon is true, so that you can practice proving without having someone to give you things. And it's useful because sometimes they end up being proofs that your lecturer was thinking of in their assignment questions. Okay, well, let's go back to our list. Anything on there that feeling a need to talk about?
Dual spaces.
Dual spaces? Sure. How does everyone else feel about that? I don't know what there is to say about dual spaces. Dual spaces?
Two space.
Okay. Let's see if I've got this right. This is my guess as to what a dual space is. Because it's always good to try and remember. So I'm going to make a guess. So if I need a vector space first, vector space over the field F. I'll use a nice blackboard bold double struck F because that makes me feel good. It's usually R. Does your lecturer use the word over in this context? Okay, good. And I reckon the dual space, oh, let's call it V. It's called V star. That sounds familiar to me. Tell me if I'm doing okay. So the vector, the dual space V star is so linear transformations like F which sends V into its own field. Something like that?
Yeah.
Okay. So we would have to define what addition and scale multiplication meant in there for this definition to make sense as a vector space. So I think we're going to need to think about that. So define F plus G. Transformation, I guess, is the official. Where F plus G of V is F of V plus G of V. Does that sound reasonable? And for M in the field, define mg as where mg of v is m of g of v. I just want to think about what's going on here. So this plus is the plus from f, because these things are, because these functions go from v to the field, which means that if I do function of v, then this f of v is a number in the field and g of v is a number in the field, and so that plus is the plus from the field. And this multiplication here is the multiplication from the field. It's not scalar multiplication in the usual sense, like because g of v is a number in the field. I don't know if that's important. But this plus is the plus in v star. So the plus in v star is defined to be basically the plus in the field. I feel like we had to do this because it's not a vector space unless we define what addition and scalar multiplication are. So I'm pretty sure that this still is a linear transformation. This one here. It's still a function that takes vectors. It's certainly a function, this function here, where I do f of v and g of v and add them together, still takes vectors in v and produces answers in the field, because that's in the field and that's in the field, and when I add it, it's still in the field. And still, if I have v plus w, the f will split over the v plus w and the g will split over the v plus w, and then you'll be able to recombine them into f plus g of v. Yes, it still works. Okay. Cool. Right. So that's what the dual space is, I'm pretty sure. Does that sound good? Okay. Cool. I have a feeling there's a word for this. Is this linear functionals? Is that what these things are called?
Yeah, F and G.
No, the phrase functional
Yeah.
as the name of this object. What a weird word. So when someone says linear functional, they mean linear transformation from the field, from the vector space into its field. Okay. Cool. Right. And they would necessarily be onto the field. That's cool. Except one of them. The one that sends everything to 0. Okay. Don't know if that's important. I was just thinking that if you had a linear transformation into the field, if it sent any vector to something that wasn't 0, then any multiple of that vector would become a multiple of the thing that wasn't 0, and that should be able to produce the whole field. So if you multiply one number in the field by everything in the field, you should be able to produce the whole field. Okay. Cool. Okay, and I guess the zero vector in this dual space is the function that sends everything to the 0 in the field. Okay, so sort of 0 in V star is the function with O of V equals 0 for all V in V, where that 0 is in the field. Okay, good. We need to know what the 0 vector is. Okay. Why do we care about this?
You mean the dual space or the 0?
Dual spaces. I don't know. How does it? Why do we care about dual spaces? That's a useful question to ask.
It's because of the transpose of a linear function.
Oh, because of the transpose of a linear function. Of a linear transformation. Okay. Well, let's do that then. I don't know what that is, but that's okay. So, you're telling me we care about this because of the transpose. You're telling me we care about this because of the transpose.
Yeah, the transpose is that from the dual W to the dual V? Yeah.
So just a second. No, I'm not going to talk about transposes yet. I want to have a better understanding of this dual space if we're going to use it to make something. So, just as an example, I just want to be sure of this. So if we had like the V was equal to like R3, then the linear functions from R3 into R is a linear transformation, right? Okay, so to be a linear transformation from R3 into R, you would need to take, it would basically be a matrix, because all linear transformations can be done with matrices if you want. So if you started in R3, you need a matrix here, you would have a vector in R3 here, and you would produce a number in R here, which is a 1 by 1 matrix. In R1, and so this would have to be 1 by 3 as a matrix. Okay? So my V star is made of these things. My V star has to be made of 1 by 3 matrices. Okay? So basically now V star is actually the set of F which send R3 to R, such that F of X equals like Vx for some 1/3 matrix V. That's basically what it is. Because all the new transformations can be done with matrices. If I'm going from R3 to R1, I have to be a 1/3 matrix. So essentially, that means that my V star is the dot product. Like I have to pick a vector V, so an object in V star is really a vector, but it's being a vector being a function because I dot it with everything, because this is the dot product matrix multiplication. Oh, cool! Okay. So, vectors in R3 are columns and vectors in V star are rows. Like vectors in inverted commas. So this is how we turn columns into rows, by going over to V star, and that's why the transpose is a thing. Okay, good, just making sure. So V is columns, and V star is rows. Right. Right, and that's why transpose would be a thing. Okay. I mean, this is just one way of thinking about it. From an algebraic point of view, they're not really rows. That's just how we represent them, but it's good enough for the rest of us to just feel okay about that. Okay, cool. So this is what I'm thinking in my head. Of course, technically, you could do V star star, and then you could have the functions from V star into R. Is that necessarily isomorphic to V again? It would look different. Oh, okay. That would get us some weird ass stuff. Okay, but that's okay. I'm feeling good about this. And so that would mean that there would be a natural way of mapping from V to V star. So in this case, V and V star are isomorphic to each other. They're just differently shaped. Like I represent them differently, but they're the same thing. Because this is a vector in V, it's just written as a row. So there would totally be, I reckon this is the canonical isomorphism you might be thinking of in one of them. There'd be a standard, most fundamentally easy to describe isomorphism between V and V star, where you could have an isomorphism which sends V to V star for this specific example, where phi of the vector V is the function where phi of V, which is a function acted upon W, is V transpose W. So basically, e.g., phi of the vector 1, 3, 2 is function which sends x to 1, 3, 2 as a row times x as a column. That becomes really hard to talk about at all and write on paper, doesn't it? If the output of your function is itself a function and you can only define it as by what it does to things, that makes it really hard to write down. This is a weird ass, like that should be a bracket there, right? If this function acted upon that vector produces this answer. Because phi of V is a function, so it goes in this position when you do function notation. Wow. No wonder this is hard to talk about. So that's a function. And this is the input of the function. And this is the output. But the function itself is the output of this function. it's easier for me to think about this as just in my head going, okay, well the vector becomes a row and that row creates a function by multiplying by the other vectors. Okay, so if rows are linear transformations and columns are vectors, then when I transpose something, it must turn vectors into columns into rows, which therefore turns vectors into functions. Okay. But we can extend this, I reckon, because this matrix multiplication is the ordinary dot product, so we should be able to create this using a Q, right? So if I had V with symmetric bilinear form Q, then I should be able to say phi sends V into V star by phi of V is a function defined by phi of V of the vector W is Q of VW. That's not a phi, that's a Q, sorry. So this produces a function. So if I do, damn it, let's just keep track. That's the V, which is here and here. This is the V star, which is this thing. This result is in V star, which is that bit there. And then this is the result of the function. So this is a function. This is the input. This is the output. Okay. So I can create a linear transformation that goes from the vector space to its field by doing Q of a specific V that I was thinking of with everything. So if I pick a particular V and do Q of V with everything else, that's a function that takes all those W's and produces a number in the field. And so this is a thing in V star, this thing. Yeah. Like the thing with that specific V in that spot and all possible W's, that's a function that's in V star, a functional. And so I can create a function that goes from V to V star by putting the V in that spot. Right. And this was me trying to copy what I did in R3, but with Q instead of matrix multiplication. Because I should be able to do that, because as far as I can tell, that's the theme. We turn dot products into Q. Yeah. Yes. I reckon this has to be a non-degenerate bilinear form, or this isn't going to work, I would imagine. I could be wrong about that, though. I don't think it would be an isomorphism unless this Q was non-degenerate. Because if Q was degenerate, then you would have several W's that would all produce the answer 0, and it wouldn't be a one-to-one function anymore, and weird crap would happen. Okay. Just making sure. So let's see if I can figure out what transpose is. Because I made a pretty bad mess of it last year in the revision seminar. So the goal is to think, well, this is what I'm thinking. I don't know if it's Nick's goal, but my goal would be to go, well, if linear transformations are matrices, then transpose is a thing I can do to matrices. And what does that do to the linear transformation? And that's what I would like to know. So that's the thing in my head. Linear transformation of the matrix. Can be done to a matrix what does it do to linear transformation? That's the question. That's what I'm wondering. Okay, so my microphone's been off most of this time, but there is one in the bench, so hopefully it'll still work. Okay, well, we just discovered that transposing a column produced a row, and the row was a linear functional. So we already have that. So we went, turns the column vector into row vector, and this was a vector, and this was a linear functional. And the reason I might be interested in this is that if my vectors aren't columns but are actually like functions or like polynomials or symmetries of a cube, I don't know, if my vectors are not things that have coordinates, then my linear functionals won't be actually rows vectors. They'll be nebulous, airy-fairy thingamajigs that I don't really know what they are. But if I can think about it in terms of vectors and see what it does to the general algebra, I might be able to see what happens when I do linear functionals from the polynomials to the real numbers. Right. Because there is one, because if I have the polynomial, all the polynomials, that's a vector space. And if I sub in 1 into the polynomial, that's a function that goes from a polynomial to the real numbers, p of 1. And it's linear on the polynomials. And so subbing in 1 and subbing in 2 and subbing in 3 and subbing in 4, they're linear functionals of the polynomials as a vector space. And so I'm going, what happens if I transpose them? That's interesting. Okay. So if I want to take, I have no idea, I'm going to have to look it up. Can you help me? Try and find transpose. But I'm thinking about this. If I have a matrix here, like an ordinary linear transformation, what that does is it takes a vector v and it produces like a vector w, which may or may not be differently lengthed, right? Cool. That's, yep. Okay. So each row of this is a linear functional. So this whole matrix, like, I'm just thinking in Rn. So this is in Rn, and this is in Rm, and this is a m by n matrix. Yeah. So each row of this is a linear functional, because I can go this row times that vector produces the first entry of this thing. So the first row is a linear functional. So if I was transposing it, that would go back to being a column vector, wouldn't it? Because transpose takes column vectors and produces row vectors, which means it takes vectors and produces linear functionals. So if I have a linear function when I do the transpose, it will go back to being a column vector. So I don't know what I'm doing. But there's something in that, like the transpose the transpose would have to be, oh crap, what is this even doing? Oh, okay. Oh, here's another thought. This times v, if I transpose the whole thing, the v becomes a row on the other side. And so the transpose matrix, if this matrix acts on vectors which go on the right-hand side, the transpose matrix must act on rows that go on the other side. Aha! So that's why the transpose has to go between the stars, between the dual spaces, because it acts upon rows. Right. Okay. So just let me think about this. If we had like AX and then we transpose, then that would be like X transpose A transpose, like that. And that would, so this acts on columns and this one acts on rows. Okay, so if that makes me think that A, this is abusive notation, but A sends sort of V to W because it acts on columns, and A transpose will have to send because it acts on rows.
I think it's W, Q,
Ah, whatever. I'll make that up in a minute, but that's my idea. Okay, I might be even ready to actually read the definition now. Okay, suppose L is in W star. L sends W to F. No, there's something earlier than this. Okay, this is making the matrix. Choose an order basis. Then it's a W. So suppose V is the span of that and the kernel. Complementary. Ordered basis. Where the hell is the transposer going to appear? What was capital L?
I think that's just the function.
Capital L. Oh, it was just, so capital L was the original linear transformation. And you can define what it does by defining what it does to each of the basis vectors. That makes sense. Choose an order basis for the image of L. Extend it to an order basis for W. And then you, okay. And then you find the things that, I'm just going to need to draw these pictures just a second. So L sends V to W. And it has an image, like that. And then we choose an ordered basis for this. and then an ordered basis for the rest as well. So that's W1, W2, W3, W4, W5, etc. And then we go over here and we choose V1 to end up at W1. That was this point here. And V2 ends up at W2. And V3 ends up at W3, etc. Okay. And you know that none of these V's are going to end up at the outside ones because all of these end up in here. Okay. V1 up to VR are linearly independent because these ones are, and the linear transformation transfers its linear combinations through back to the original. Okay, cool. Okay, so over here, span them, and then anything in the kernel of L won't be here because these ones weren't 0 afterwards. Okay. So the kernel ends up here at 0. Beautiful. Okay. So I'm up to here. So L of V is some linear combination of these W's, which, because linear transformations is some result of the linear transformation of something back in V. Well, that makes sense. If it ended up in here, it had to come from here. Okay. All right, so he's proving that the kernel is complementary. That's fine. Choose a basis for the kernel as well. Okay. With respect to these ordered bases, the matrix ends up being this. Cool, that makes sense to me now. All right, I now know what he's doing with those bases. So what we've done is we've chosen a basis for the image of the linear transformation, work backwards from there to pick a basis to get some linearly independent vectors there. Chosen the complementary subspace of this is the kernel of L. And that has a basis as well. And all of these end up at 0, and these ones end up at the W's. And nothing ends up at these places, but that's okay. Okay, so we've got that sort of L of V1 is W1, and then L of like V, however many there are. We haven't got an N. Is it N? R. It's WR. And then L of the rest of the V's is 0. For VI not in the span of, well, for VI in the kernel, right? Okay, and so if we're going to write everything in terms of these bases, this would be 1, 0, 0, 0, 0 because it has 1 W1 and 0 of the rest of them. Okay, so if we write them as coordinates based on these bases, we get that matrix. Okay, cool. I think I understand what's going on there. And so now we're saying, suppose little l is in W star. So it's a linear functional from W star to F. Then L composed with big L, sure. So if L goes to there, then if I do L from V, then L composed with big L is this. That's that function that goes from V. This goes from V all the way to F via W. Okay, good, good. And so therefore this is in W star and therefore this is in V star. Okay. And so now that's saying that everything that L is creating a function that goes from W star to V star, according to this. Yeah. So now there is a function, I think, I'm not sure there, but I'm pretty sure we're doing that L transpose sends W star to V star by L transpose of L, which is in W star, is that. I think that's what L transpose is. Could be wrong, but that seems reasonable. It's a perfectly good function that goes from W star to V star, and it's based on what L is. So the assignment which does that is linear. So a linear function from V to W induces a linear function from W star to V star. Some people call this the dual, but we'll call it the transpose. Oh, that's way better than last year's definition. Okay, I want to see what this looks like for a real, like in R3. So in R3, that V is going to be R3 and W is going to be R2. All right? And we're going to have L of X, Y, Z is going to be like that. That's what L is. It's a linear transformation. Sends V to W by that. Perfectly good linear transformation. And so V star, so let L, which sends W to R, so yep, be the function where L of X, Y is like 1, 2 times X, Y. That's a perfectly good function. So we're saying that what L transpose does is it sends this to something in V star. That's what that does. Okay. So L transpose sends W star to V star. Okay. L transpose of L is L composed with big L. I mean, that's what we were told what it was, right? Okay. Well, let's just see what happens. This should be a function from R3 to the field. So L, that's a function. That's a function from R3 to R. We know that. And it should be L of the vector x, y, z, right? Should be L of x, y, z. And that should be L of 1, 2, 0, 0, 1, 1 times x, y, z, because that's what L is. And little l should be 1, 2 times this. Okay, which is this? Which is a perfectly good function from R3 to its field. Okay, And this is the key bit here. To figure out what L transpose, so L transpose, like if L was represented by 1, 2, then to get what L transpose did to 1, 2, I had to multiply it by L on the right-hand side. So if I was thinking of L as being written in terms of a basis, I would normally think of it as a column vector. That's the key that makes it a transpose. If I wrote little l as a basis in terms of 1, 0 times xy and 0, 1 times xy, I would normally write it as a column vector if I was trying to do it as, ignore all of its, whatever, the fact that it's a function, and say, ooh, it's a, I'll change the shape of the brackets, but I can represent any vector space as column vectors of the coefficients of a basis. And so I could actually think of 1, 2, xy, which is what L was, that function, would become therefore the vector 1, 2. And then L transpose of L would be the vector yes. Right, so the reason it's transpose is because if you want to look at your elements of W star as a vector space in their own right and write them with coordinates, you would use column vectors. And so if you want to act upon those column vectors, you're going to need to use the transpose of this matrix. But if I want to keep thinking them as row vectors, I just put them on the left-hand side of the matrix instead of the right, which is a transpose way of doing things. So L acts upon the vectors in V by multiplying them on the left. So L acts on column vectors by going matrix L times vector equals output in R2. L transpose acts on row vectors by it going here. Like that. Right. Well, I feel better. Not 100% better. There's a lot of stuff going on. There's a Q involved here that I'm not really sure on. And I guess that Q comes in when I do this matrix multiplication. There's all these Q's there. Like this matrix multiplication was done, if I was done with like all these dot products. So I think there's a Q. I have to work the Q in there somewhere. But essentially, there's a natural isomorphism between V star and V, which is turning rows into columns and turning columns into rows. And under that natural isomorphism, matrix, what the original vector, what the original matrix did to vectors by multiplying on through the matrix on the left, it does that to the functionals, which are row vectors, by multiplying on the right. Feeling better, not completely, because I don't know how the Q comes into this yet. Yeah. Yeah, okay. And I would really like to do something with this from a perspective of a vector space that wasn't Rn to see what it looks like there, but I'm not 100% sure if I want to go there or not. Your lecturer doesn't seem to have spent all that much time living in like the polynomials if he wanted to. Did he do that in some of the tutes or something? So I don't know what this would look like if I was trying to not think in vectors. Yeah. Let me see if I can do it. do real polynomials of degree up to 2. So there's a linear transformation from, let's do this as P2. Let's P1 be the real polynomials of degree up to 1. There's a linear transformation that goes from P2 to P1, which is differentiation. Like that. So I'm wondering what L transpose is. That's what I'm wondering. So, yeah. So if, okay, that's just, differentiation. It's a perfectly good linear transformation that goes from the degree 2 polynomials to the degree 1 polynomials. And L by L of Px is P of 1. That's a perfectly good linear transformation from the linear polynomials to the real numbers. Sub in 1 and see what you get. Because if I sub in 1 into the polynomial, which is 2 times the one I had before, I'll get 2 times whatever I got the first time. And if I add 2 polynomials together first and then sub in 1, it's the same as subbing in 1 and then adding them, so that's all good. Okay, so I want to know what is... It would be really cool if it was just subbing 1 into the original one, but I have a feeling it won't be. I have no idea what's going to happen here. I just wanted to see. And I probably need to choose a Q, unfortunately, to make this work. But presumably it should be that, right? According to what his definition is. Which looks like, to me, so L of a polynomial, I shall call it Q, for Q of x in P2. No, P1, P2, yeah. Should be L which should be L of Q dashed, yeah, which should be Q dashed of 1. It seems reasonable. I don't really get what's going on, or if anything's happening at all. It looks too obvious, like, well, but that's what the transpose is. So it looks like L transpose does to subbing into, yeah, I really don't know what's going on. Like, that's what it says. So, subbing into 1.
He uses then the transpose to
Right.
And so
Adjoints belong to
if it's earliest from V to W, the adjoint earliest just from W to V.
okay.
So it'd probably be the next section.
So, and the adjoints is where all the Q's come in.
Yeah, because you go from, I'm going to go all the way around, so if you go from L, it goes from V to W.
Okay. What lecture was that we were just looking at? I lost it.
Just go down to 23, so one of them will be called adjoints, and that will be the one.
So in this one, you had V, L. We wanted something with it which was as small as possible. So this was projection, right?
Yeah, I think if you go down, he's going to introduce it later.
Yeah. So the general. I was just trying to figure out what the goal of adjoints was.
Yeah, I think he's going to be further down. We had this
Yeah.
your example, similar to yours. Yeah.
So I saw in one of the other lectures, or not lectures, one of the things he did last week, he then drew another arrow from V star to V, so it was kind of the inverse then.
Hmm.
Q to V there to get us all the way around from W to
So the adjoint L star, which comes from W back to V, which is what I would like. I mean, the transpose does that. Like if I transpose the matrix, then multiplying by a column brings it back the other way.
the transpose would actually just go from the dual to the dual of the other.
No, it's all right. So the transpose goes between the duals, and that wasn't. We didn't really transpose the matrix. We just put the row on the left-hand side and the columns on the right-hand side. So we're wanting to have the idea of literally transposing the matrix and acting it on the vectors. That's the idea of the adjoint. So we had the transpose acted upon the row vectors, but we would like a linear transformation that acts upon the column vectors in the same way that the matrix transpose acts upon its column vectors. And so the only way to do that is to have a map that goes from W to W star. Now we just had a map which turned a row into a column, but that's not really a thing. Like we need a proper map that goes from W to W star, and the way to provide that is with one of these Qs, like I did before, where I went Q of V and W, and all the W's is a function from the W's. Right, okay. Okay. And so the conclusion here is that L star is characterized by the dot product in W. So V has come into W via L, and then it's dotted with a vector W in big W. And it's the same answer as staying in V and bringing W back. That should be a W there, I reckon, not a V. All right. Bringing W back to V and doing the dot product back in V. Okay. And dot products, the traditional dot product is literal matrix multiplication. Just want to, just a second. So I think this is as stupid as it looks. It is exactly as it looks. but it's the adjoint that's the really interesting one. So we have a V going across to a W, which is what L does. Like that. So in Rn, with the traditional dot product, so with the traditional dot product, L of V is matrix times V, right? And then when you dot that with W, you put the W as a row vector. That's what this is. And they're saying it's the same thing as doing L of W, so the W is on this side, and putting the V as a row here. All right. And so this L star would have as its matrix L transpose in the traditional dot product. So this is where like A, B is A transpose B, right? Write it as a row and a column. Right. And of course, the transpose of a 1 by 1 matrix is the same. And so these have to be equal. Right. So basically we could ask ourselves in Rn, the question is, what does this matrix here have to be in order for this to be true for every V and W? And the answer is it has to be the transpose of L. But then we're asking ourselves, what does L star have to be in order to do that? And L star has to be, it has to have the transpose in there somewhere, but it has to be, it's sort of mangled a bit by the kind of dot product you're using.
If you go back up on those, how does that line up with the right underneath where it says define the adjoint? It has L star is equal up here. As L star is equal to the inverse of QB.
Yep.
So is that sort of withdrawing?
That's what I'm trying to do. I'm not sure what's going on yet, but QW well, let's see if we can match it up. So L star, so this is a vector in W, right? So we have to turn that vector into, oh sorry. Here. So this it's a function, right? So we have to do this here. So this bit here was L star of W, right? Okay. So Q of W is the function that goes from, is the bilinear form. Just a second. What is QW?
QW in that graph, yeah, with the isomorphism between W and star.
So in our case, that was, we're thinking of this W as a, this was a column, and this QW would be thinking of it as a row, because now it's in W star. And then L transpose is